on. Hey everybody. As I look over this week's assignment, there are lots of questions, but they're on basically what we've been doing over and over in class. Basic ideas about energy and potential and a little bit about capacitance. So I feel like I've shown you a lot of the things that you need to be able to do this assignment, at least easily, but there's still a few of them that I feel like maybe a little bit of walk through some of the explanations might be pretty good. So I have all the questions that we're going to be doing listed below at the bottom. They're from chapter 25 and 26. So let's start. 25.26. Okay, so 25.26 goes like this. Some equipotential lines surrounding a negatively charged object are shown in figure blah. What's the potential difference between any two, where the potential difference between any two adjacent lines is the same? In which region is the electric field magnitude greatest? What's the direction of the electric field in that region? Okay, so, well, let me try to recreate this diagram. Get a minus sign. Looks kind of like that. Okay, so these are equipotential surfaces. The first question asks, where is the electric field strongest? I want to emphasize something in the relationship between equipotential surfaces and the electric field, right? So the idea here is that if you travel some distance, I don't know, between two of them, whatever, delta x, okay? According to what we've been talking about in class, the change in the potential is going to be minus delta x dot E. Okay. So we've used this in a variety of ways, and they're fairly useful. But there's one aspect of this that I really want to emphasize here, which is that there's a relationship between the spacing between the two lines and how strong the electric field is. We can interpret visually how strong the electric field is by looking at the spacing. What do I mean by that? I mean that, let's see, this is a little bit too big. How about that guy? We mean that we know that in the case of this diagram, the difference between any two lines here is the same, delta V. If the distance between them is large, it must be because the electric field is smaller. And similarly, if the distance between the two adjacent lines, like over here, if that distance, the gap, the spatial separation between them is small, it must be because the electric field is super, super large. Another way to think about this is that if the electric field is really, really big, your potential is going to ramp up very quickly. But from this, we end up with something fairly nice. You can tell, oh, geez. Delete. You can tell, oh, maybe I'll just stop doing that. You can tell based on the spacing of the lines how strong the field is, or at least where it's strongest. One way to think about this is in terms of like the slope. You can interpret these equipotential diagrams the same way you would interpret like lines on a topographical map. Right? So on a topographical map, each line represents the same altitude, which corresponds to equipotential lines in terms of the gravitational potential energy. But on a topographical map, each of these represents a constant altitude. When the change in altitude, like over here, is really, really close together, it means that you're dealing with a really steep hill. And if the lines are really, really spread out, as they are over here, it means that you're dealing with a fairly shallow rate of increase. So let's answer the question. In which region of the electric field is the magnitude the greatest? So where's the electric field strongest? It's probably strongest over here, where the lines are closest together. A little bit to the right of the thing. What's the direction of the electric field in that region? Well, if I knew what the value of these equipotential surfaces were, I could probably suss out the strength of the electric field. But I don't have that information on me. What I do know, however, is that... Oh, geez. What I do know, however, is that these are all generated by negative electric charge, and that means a positive chest charge would feel a force in that direction, right? And that means that the electric field must be pointed in that direction also. Which equipotential line has the greatest potential? I wonder. Well, one way to think about this is like the equation. The closer to the charge you get, the larger this number becomes. It becomes a very, very large negative number as the distance gets closer to zero. So I think that the equipotential surfaces closest to this are probably the largest potential value. Okay, so let's move to the next question, which is 25.27. I don't want to give all of these particular questions away. This particular assignment's just chock full of little understanding questions. Because it's important that you understand. A lot of people try to get through these courses without actually learning what I'm trying to teach you. You know, you can kind of fake your way through it, looking up equations and stuff, guessing answers until you run out of tries, maybe stumbling on the right one, asking somebody else to do it for you. I want you to understand this because it's elegant. It's an interesting thing to learn about. So, yeah. You determine that it takes no electrostatic work to move a charged object from point A to point B along a particular path. Can you conclude that A and B are on the same equipotential surface? This question is bonkers. It's a little bit mathematical. The question here is, can we imagine a setup where two places have the same potential but aren't on the same equipotential surface? What does it mean to be on an equipotential surface? All right, well, here you go. There you go. There's an equipotential surface. What does it mean to be on an equipotential surface? The idea is that you can move from one point to another point, and the whole time requires no effort. Every point along the way, it requires no extra energy. So you can go this way. No extra energy is required to get to here. No extra energy is required to get to here. And one continuous path between the two. Is it possible to imagine a scenario where you have two equipotential surfaces, two equipotential points, but they're not on the same surface? Well, for that to be true, somehow there would have to be like maybe a break between the surfaces that they were on. Maybe this one is on one surface and this one's on another surface, and these two surfaces aren't connected. Do you think that's possible? Well, earlier I was relating equipotential surfaces to like topographical maps. Topographical maps. In a topo map, each line represents constant altitude. So is it possible for two places to have the same altitude relative to, I guess, sea level, where there's no way to get from one point, right? So these two are on the same altitude level, and that means that you can walk from one to another, keeping at the same altitude. We live in British Columbia. It's lovely. It's a land of lakes and valleys. You can imagine a valley on one side here with a lake in it, and a valley on another side here with another lake in this one. And this lake has the same altitude as this lake. Just because they have the same altitude, what does it mean? It means that if you could get from one to the other, the total energy required would be 0. On the other hand, if I'm going to travel along a line of the constant altitude, I'm going to just go around the lake. If I go on a line of constant altitude, I'll be stuck on this lake. I can't get to this lake from this lake without going to a different altitude because they're separated by valleys. So arguably, you can come up with a similar scenario in terms of equal potentials, where two places have the same potential, but neither is approachable by the other. Like, so for instance, if I had a charge plus 3 coulombs and another charge over here plus 3 coulombs, the equipotential surfaces in this case would look like this. Is that right? Yeah, I think that's right. Anyway, moral of the story is this surface and this surface both have the same potential, but you can't get from one to the other. All right, well, anyway, that's that answer. B, can you say the path is part of an equipotential surface that includes A and B? Oh, okay, so earlier they mentioned a path. All right, so the idea here was, here you got a point here A, point here B. They are on different equipotential surfaces. Fine. V is equal to 10 volts. V is equal to 10 volts, whatever. Is it possible to get from one to the other? Can you definitely say that the path that takes you from one to the other is part of the equipotential? That's what the question's asking. Can you say that the path is part of an equipotential surface that includes A and B? And the answer is no. No, you can't. Why can't you? Well, we know that these two aren't on the same equipotential surface because that's literally what we're talking about, right? And if they're not on an equipotential surface, it means that that there doesn't exist a path from one to the other where the thing's energy doesn't change, right? So if I move along this equipotential surface, my energy doesn't change. If I move along this equipotential surface, my energy doesn't change. So this isn't on an equipotential surface, so its energy must change, so it's not equipotential to the other two. All right, well that's fun. Next question is a tutorial question. So in these setups, there's there's these tutorial-y type questions where it kind of leads you through the thing, and they're not in the textbook, but I thought this one was pretty good. It goes, energy stored in a configuration of particles. And it said that there were 4 charges. Each of them had a total charge Q. Looked like that. And they were arranged on a box where the length of the side is L. And it said the total energy is KQ squared over L. Q minus Q. Oh, it says that it's proportional, so it's KQ over L times a term. And then it was asking you for that term. So in this life, there's all sorts of situations where you can be all sorts of tricky to figure out these answers. This isn't really one of them. In this question, you're probably better off just calculating the energy symbolically. So to do that, I mean, we give these labels. There's A, B, C, D. And this is what we talked about in class. You can calculate the amount of energy it took to build the system, step by step. So let's do that. So step 1, there's nothing, and then we bring A into place. and that took energy 0. Okay. Step 2. A is in place, and it's making an electric field, and then we're going to bring B into place. Okay. The change in the potential for particle B is going to be Q, which is the charge of A, times K divided by L. L is the distance between them. Okay? So the energy it took to do so is going to be Q, which is the charge on B, times, so it's going to be Q squared K over L. Okay? And now we continue. Step 3. You already have A and B in place. L. Now we're going to bring charge C in. Charge C's change in potential is going to be the potential from A, which is Q times K over this distance here. What is that distance? It's square root L squared plus L squared, which is square root of 2 times L. So that's square root 2 times L plus charge on B times K divided by L. Okay. So that energy is going to be Q times QK over square root 2L plus QK over L. So that's going to be Q squared K over square root 2L plus Q squared K over L. So now we have A, B, and C in place. And we're going to bring charge D in. Okay? So the change in potential for this one is going to be L. So that distance across is going to be square root 2 times L. All right. So that energy is going to be the potential for the first one plus the potential for the second one plus the potential for the third one. Okay. And so the energy required to bring this one in place is going to be minus Q times QK over L plus QK over square root 2L plus QK over L. And now we can add up for the total energy. So the first one took no energy, and the second one took Q squared K over L. And the third one took Q squared K over square root 2L. And the fourth one took Q squared K over L. And the fifth one took minus Q squared K over L minus Q squared K over square root 2L. And then minus Q squared K over L. And now you play a cancel game. Let's see, this one cancels with this one. And this one cancels this one. Whoa, the total energy to do it is 0, which is bonkers. Don't you think that's weird? I think that's weird. I think I did it right, though. Weird. Anyway, isn't that fun? That's fun. I had fun. Next question, 25.37. It goes like this. 4 possible paths for a positively charged object traveling from 2 volts to a 3 volt equipotential are shown in figure blah. Rank the paths in order of the electrostatic work done on the object along each path. Greatest value first. So that's V axis. That's 5, 4, 3, 2, 1. Here's where it starts. And D looks like that. C looks like a straight line. And A looks like that. And B looks like this. Alright, so this is fun. We want to rank the work done in moving the particle from one to another. And rank, we don't need to calculate, we want to rank it. So the work is equal to minus Q, the charge on it, times the change in potential. Okay? But in each of these cases, A, B, C, and D, in each of these cases, the change in potential is just equal to +1. So in all these cases, the work is going to be the same. Isn't that wicked? It's because the electrostatic force is a conservative force. That means energy is conserved, which means that in these cases, it doesn't matter which route you take between the start and the end point. The only thing that matters are the start and the end points. And these endpoints are all along the same equipotential surface, so it takes the same amount of work regardless. All right, next question. Here's one question. Why does my iPad think that it's 9:41 a.m.? 26.09. I wonder if anybody's watching. Anybody watching? Oh, 3 people are watching. Hey, everybody. If you have any questions or things you'd like me to go over or explain in greater detail, feel free to fill them in the chat window. Cool. Okay, let's move to the next group of questions. 26.09. Capacitors. Okay, so we talked in class about the different ways to reason your way through these capacitor questions. The one was called direct reasoning, and the other was called algebraic reasoning. Direct reasoning, you kind of think about the different issues at play, and then tell the story of why things would change. And in algebraic reasoning, you just do the algebra, and then you compare the first algebra system to the second one, and then go from there. I don't care which one you use. I think I'd rather use direct reasoning, but at this point, placing the game, algebraic reasoning is pretty cool. Question 9 says, the plates of a capacitor are charged using a battery, and they produce an electric field across the separation distance d between them. The 2 plates are now pushed together to the separation of d/2. The pushing together can be done either with the battery connected or with it disconnected. Which way would result in the greater electric field magnitude, and by which factor? Okay. So, there are a lot of things at play here. There's the geometry of the plates, the gap width between them. There's also the potential difference and the charge. So in doing these questions, what you have to do is you kind of have to suss out which of these terms is going to be the same and which one's going to be different. And this particular question is extra tricky because it's asking you to do it in 2 different ways and compare. So it says in the first one, you leave the battery connected. And in the second one, the battery is disconnected. So how do we do this? Before you go any further, if you disconnect the battery, it means that the charge is going to be stuck on the plates. And if you leave the battery connected, it means that before and after, the electric potential between the plates is going to stay the same. So how do we answer this question? Well, let's try it with direct reasoning first. So when we reason our way through it, the idea here is that there's a chain of arguments, okay? Right? So the idea here is that there is a charge on both plates. This means that there's going to be a charge density, which is determined by the charge on the plates, but also on the area. There's a charge density, and that means that there's going to be an electric field between the plates, which is going to be sigma over epsilon naught, according to Gauss's law. Because there's an electric field, there's going to be a potential difference. Delta V is equal to E times the gap width. So that's the potential difference across the gap. And then there's the sense that there's electrostatic equilibrium. Delta V gap is equal to delta V from the battery. And so the idea here is we want to apply this chain of reasoning to track how modifying the system is going to change it. Oh, come on. I just want the same copy of both on either side here. All right. Copy. Paste. Okay. So if you leave the battery connected, then the charge can change, but the potential drop is going to be the same. Okay? If the potential drop is the same before and after you squish them together, then D is going to half, and that must mean E has to double for the potential difference between the plates to be the same. Okay. So already, without going too far, we've answered the question. If you keep the battery connected and you push the plates together, that's going to double the strength of the electric field. Let me reiterate that. The idea here is that we're changing the gap distance. This number, the potential difference, needs to be the same as the batteries, right? Because you're keeping them hooked up together. So this number must be the same. And so as this number changes, this number must change so that when you multiply them together, it's the same. Okay? Which means that if you keep the battery connected, the charge density is going to double. And that means that the charge on the plates will also have to double. And that's an interesting thing. It means that you've doubled the capacitance, but don't worry about that now, because this particular question is about comparing if you leave the battery connected before you make the change versus if you leave the battery disconnected. All right. So, long story short, if you leave the battery connected, you're going to move up that way through our list of relationships. If you leave the battery disconnected, the charge is going to be stranded on the plates, and we move that way through the list of relationships. Okay? So the charge, if it's disconnected, is going to be the same. The charge density is going to be the same because the area of the plates is the same. We haven't modified that at all. And that means that the electric field is going to be the same. Oh, well, this tells us what the electric field is. It's going to be the same as it was before. If you leave the battery connected, the electric field doubles. So in this case, the electric field has to be the same. In this one, it's doubled. So if you leave the battery connected, it's twice as large in the end as if you hadn't. That's fun, right? Okay. Is that it for this question? Yeah, it's asking by which factor. Which one would be bigger? This one. By which factor? Factor of 2. So that's fun. And you might wonder how a person would go about using algebraic reasoning to answer this question. So let me go through that set of reasonings. Okay, so if memory serves, the way the arguments went before, okay, I'm really fond, if you haven't noticed, I'm really fond of doing derivations. And the reason I'm really fond of doing derivations is because you tell yourself a little story, and that story is the story of the explanation of the physics that we're doing. So they're really helpful in various circumstances. I can't, off the top of my head, remember for me that equation for parallel plate capacitors relating the two things, but I can walk my way through it. The idea here was you had some charge on the plates, and there's the charge density on the plates, and the electric field was related to the charge density divided by, oh, not 3, epsilon naught. There you go. So the potential difference is going to be Q over epsilon naught A times the gap width, D. Okay, and that's our equation. So the question here is, if you leave the battery connected versus if you disconnect the battery, how does this change? So we're going to use these equations. We're going to use another one on top of this as well too, though. The other one we're going to use is the electric field is going to be either delta V times D, no, over D divided by D. Or alternatively, the electric field is going to be Q over epsilon naught A. Okay, so how are things going to change if I change the thing? Well, in this case, there's the equation. I'm going to leave the battery connected, so before and after. Before, our equation looks like this. E initial is equal to delta V battery. Okay, how about the initial? Delta V initial over D initial. After, E final is equal to delta V final over D final. And now I talk about the relationship between the two. I know that D initial divided by 2 is equal to D final. And I know because they're hooked up to the battery, delta V initial is equal to delta V final. So let's put these together and compare them. E final is equal to delta V initial, 1/2 DI, which becomes 2 delta V initial over DI, which becomes 2 EI. Just like before, we argue that the electric field must double. What about in this case? This particular question is actually pretty tricky to do our algebraic reasoning to, because the thing that we're modifying isn't this equation specifically. It's these two equations. We're modifying a capacitor, but essentially we're coming down to the same thing from above and below in terms of variations of it. All right. Well, long and the short of it is, I don't know if you should probably get good at using both types of reasoning. Okay, so before E initial is equal to Q initial over epsilon naught A initial, and then after E final is equal to Q final over epsilon naught A initial, A final. So the idea, what I mean to say is, to do it before, we need to know to use this equation. And to do it after, we need to know to use this equation to compare them. They're both arrived at. The electric field depends on how much charge there is on your system, the charge density, but it also depends on essentially what the potential difference is, what the gap distance is. So, because I know that, I'm allowed to do this. Okay, so how do things change? The battery's disconnected, so the initial charge is equal to the final charge. Okay, and the areas are equal. So that means the final electric field is equal to the initial over epsilon naught A initial. Oh, hey, look, that's the initial. So we say, hey, look, if you do it this way, the electric field doubles. If you do it this way, the electric field stays the same. Which is the same conclusion I arrived at the other way. Pretty fun, huh? Okay, 26.15. 15. When two parallel plates separated by a distance d are connected to a battery that maintains a potential difference in magnitude d between the plates, a charge magnitude q accumulates on each plate. If the plate separation is increased to 2d and the battery is replaced with one who has potential difference 2v between the terminals, what's the new charge on each plate? Oh, this is lovely. So congratulations. This first example I did with you was an example where direct reasoning was more useful. This is definitely a case where algebraic reasoning is more useful. So, two parallel plates, distance d, voltage V, charge Q. I guess initial. All right. So it goes like this. V is equal to di times qi. I guess that's a minus q. BTW. Qi over a epsilon naught. And then afterwards, okay. Then I'm going to increase this plate separation to be wider. I'll call it D2 and V final. D final and V final. Q final, Q final. So V final is equal to D final, right final, F times Q final over A final times epsilon naught. Okay? And now we're going to relate the two sets. So in this case, V final is 2V initial, I believe. Yeah. And D final is 2D initial. Yeah. And A final is equal to A initial. So then this equation all becomes, I'm going to get rid of that. It all becomes 2V initial times 2D initial times Q final over A initial times epsilon naught, which says that V initial is equal to D initial over A initial epsilon naught times QF and now you're going to compare it with your original equation. We want to compare QI's, so so di qi over ai epsilon naught is equal to di over ai epsilon naught qf. This side of the equation is this, and then this side of the equation I just replaced for the vi. Okay. And then you play a canceling game and you see qi is equal to qf, which is really fun, right? All right. Well, nobody's asked any questions, so that's it for today's online office hours. These are pretty fun questions. Bring your calculator to Monday's class because we've got all sorts of really cool calculations to do. I'll talk to you later.